Welcome to this fifth lecture video for Physics 4A. In this set of lecture videos, we are going to look at some details regarding the forces we introduced in the last lecture. These details will be important as we start the force analysis problem-solving techniques in the next lecture. The first video you will see is my types of force lecture. It is meant to help you identify all the forces and only the real, actual forces in a given situation by highlighting the fact that all but one of the types of forces you will see in this class are contact forces. Do please watch it carefully as we will refer back to it throughout the semester. Then we will illustrate a couple examples of free body diagrams and point out a few things to watch out for as we identify the forces to draw on the free body diagram. The free body diagram will be the main graphical problem-solving tool you will see for the next few sets of lectures. As we start on the standard strategy, the approach we teach for tackling force analysis problems. The elevator simulation video uses the free Algodoo simulation to illustrate the role of the normal force in how we feel gravity, that is, weight. And finally, we will end this set of lecture videos by highlighting the difference in how we handle the static and the kinetic friction forces, and some common mistakes that students make in physics problem solving when static friction force is involved. In this video, we will talk about different types of force. So we just introduced the force in connection with Newton's laws of motion. We talked about forces as being a push or pull. That's a good starting place. Really, force is most basically understood as a push or pull. And what I think will now help us to get a solid grasp on these types of push or pull is to go through an comprehensive and exhaustive list of forces that you will see in this class. Going through this list will especially be helpful as you work through the Newton's law problem-solving strategy. The first step in that problem-solving strategy is drawing a free body diagram and knowing the complete list of forces that could be in that diagram is helpful in one, making sure that you include all the forces, and two, making sure that you don't include anything that's not a force. So let me point out each of the forces that you will see in this class, and maybe I'll say something brief and unique about each force. Okay, so let's get started with the normal force. It's the first of the forces listed as common forces. And with the normal force, there's quite a bit of detail that you can get into, which your textbook does. It describes how when you place an object on the table sags a little bit, and normal force is produced with the sagging deformation up until when this normal force is equal to 8. It's good to have that mechanism in mind. And really, with the normal force, the most important thing to understand is that it's the contact force that's perpendicular to the surface. So when I put my hands together, there's a reason my right hand doesn't go through my left hand. And the reason is the normal force produced by the surface on my right hand. So that's normal force. You will see it in quite a few contexts. In some situations, we ignore its existence. And in other situations, we make sure we include this force in our analysis. The types of situations where we have to make sure that we include normal force will often involve a friction force, which your textbook covers in the next chapter. So we'll talk a little bit more about friction force in a couple weeks. And for the time being, I guess what's important for me to say is that the direction of friction force is parallel or tangent to the surface. So when you think about contact forces, forces that are produced when two things touch, there are two types of forces we talk about. There's the force that will be perpendicular to the surface, that's the normal force, and there's a force that will be parallel to the surface, that's the friction force. Between these two, they cover all the contact forces that occur between two surfaces. And we also bring in a couple more contact forces. They are covered in chapter 5 under common forces. And although they are somewhat related to each other, I think it's important that we treat them as separate. So the first of those remaining contact forces that your textbook will mention is the tension force. So tension force is, as your textbook says, it's a pulling force that acts along a stretched, flexible connector or a rope or cable or string or sometimes maybe even spring, although spring force is the second force that we will treat separately. If you think through materially how a rope exerts a tension force, the way it works is quite similar to a spring force. So as you pull on the rope stretches a little bit, and as it's stretching, it pulls back on the thing that's pulling. That's the tension force. In terms of problem solving in this class, I think the most important thing to remember about tension force is it gives you two things that are connected by string at the same distance, and the amount of tension force is whatever it needs to be so that that distance remains the same. Up until the point where the string is no longer taut and it goes slack. And this is what the textbook is getting at with you can't push a rope. Tension force can work only one way. It resists the pulling and it doesn't resist the pushing. That's the job of the normal force. Spring force is something that we'll spend more time in coming weeks, especially as we talk about work and energy. And for the time being, I guess it's enough for me to mention Hooke's law that relates the magnitude of spring force to the displacement, how much the spring is either stretched or compressed. And we'll talk more about spring force later on in the semester, so we will leave that there. Okay, I think that covers all the contact forces that you will see in this class. And this is the great thing about contact forces. In order to exert contact force, two things must be touching. Either two surfaces are touching, so there's a normal force and or friction force between these two surfaces, or there's a string attached, and the string is taut, so there's a tension force, or there's a spring attached, and there will be a spring force. These four forces that I mentioned, you can't have any of these forces acting without there being some kind of contact. So it limits what kind of things you look out for. And even some other forces that we won't really deal with much, like air resistance, or sometimes called air drag, those are also a type of contact force. It's like a friction force. Air resistance only acts when air is touching the object. Now, we do have forces that act at a distance. And for the purpose of this class, we will really have only one force that acts at a distance, and that is gravitational force. We bring it in chapter 5 as a weight, which is, as far as this class is concerned, it's another word we use for gravitational force. And for a great portion of this semester, we'll treat gravitational force in a relatively simple way. We introduce this quantity called gravitational acceleration, or maybe less confusingly, strength of gravitational field. And given this quantity g, the gravitational force is given by mass times that gravitational field. And this description is perfectly fine as long as you are near the surface of the Earth. Now, when you are farther away, maybe you are in orbit, maybe you are, maybe we are talking about interaction of astronomical bodies in a solar system. Then at some point, we do need to bring in Newton's law of universal gravitation. That's in chapter 13. And I think it will be useful to bring this in after we've talked about all the other mechanical aspects, things like energy, momentum, angular momentum. So we'll hold off on this longer description of gravity. And for the purpose of this class, gravity will be the sole and only force that can act without touching. Now, if you know a little bit about physics, then that's not quite right in the real world. We have electric force and magnetic force, but those are the subject of physics 4B. So, unless we explicitly mention them, you can assume that we are not going to deal with the electric or magnetic force. So, I think this listing of forces will help limit the number of forces that you will need to consider. You know that as you draw free body diagram, all the forces that you might be drawing on a free body diagram, they will either have to come from something that's touching the object, or it'll have to be gravity if it's coming from something that's not touching the object. So let me summarize. This is the comprehensive list of different types of force in physics 4A. We have the normal force, we have friction force, we have tension force, we have spring force, and finally, we have gravity. Oh, I said I would point out a unique thing about each force. So the thing about normal force is it prevents sinking or digging in of an object into surface. The thing about friction force is it can be complicated, but it boils down to it prevents sliding between surfaces. Tension force, which only acts when two things are connected by a flexible connector or string, it prevents two things from getting farther away, moving farther away. And for spring force, I guess the best thing for me to say is Hooke's law. Force is proportional to the displacement by some constant, spring constant, and in the opposite direction from the displacement. Sometimes we talk about restoring force. And for gravitational force, which we'll talk about more, for now, the important thing is it's given by mass times the strength of gravitational field or gravitational acceleration. And the important distinction to draw here is that all these forces, the first four forces that I said in blue, are contact forces. And there's only one in the list that is not a contact force. So, for example, if I have an object and right now something's touching it, so there are contact forces on this pen. If I set up situations so that nothing is touching this pen, there can really be only one force on it, which will be gravity. So if I let go so that nothing's touching it, then the only force on it is gravity, and we say it's the gravity that's accelerating it downward. Now, this isn't to say for gravity to act, nothing can be touching it. So while this is resting on my hand, gravity is still on it. In this situation, gravity is pulling it down, but the normal force from my hand is also pushing it up. So they balance out and it's not accelerating. The net force is equal to zero. So that's enough of the different types of forces. I just wanted to close by highlighting a couple things that are not distinct types of forces, especially in physics 4A. One is something that you will see quite soon, which is called centripetal force. And people in this class might have heard a caution against centrifugal force. And what I want to caution you in addition to that is that centripetal force is not a separate type of force. If you read through the section carefully, you will note that it says any net force causing uniform circular motion is called a centripetal force. So a centripetal force is a type of net force. It's a kind of subcategory of the forces that you get when you've added all the forces that's acting on a body. So and as you're trying to count up all the forces acting on a body, you don't count the centripetal force as its own separate force, because centripetal force is what you might get after adding everything together. It's not one of the ingredients that go in. And the thing about the centrifugal force, it has to do with the inertial reference system. And I think it's best discussed in discussion of Newton's first law. And I will just leave it here, which is that in this class, we will always work with the inertial reference system. So any pseudo forces or fictitious forces that arise from the acceleration of a reference frame, we won't deal with them. There's a lengthier reason I should give why it's good for us not to deal with the centrifugal force, but this video is already long, so I'll hold off the discussion until later. And with that, I'm just gonna go to the textbook section and just look for situations that involve forces where I could maybe draw a free body diagram. Oh, this is an interesting situation. So let me draw a free body diagram here. The situation is described as someone was transporting a box of cupcakes. Okay. So I have a box of cupcakes. The car in front of her stopped suddenly. She applied brake immediately. She was wearing her seatbelt. That's our physical. Okay, okay. So I guess the easiest thing for me to do is imagine this box of cupcakes resting on the seat. This is the seat of the car, and the larger car. I'm not quite drawing. So initially, this whole thing is moving with some velocity. And at some point, suddenly she has to stop. She applies the brake, and the car stops. So that means that there's some that means that there's some backward acceleration. I think, yeah. So that initial velocity comes to final velocity of zero. Okay, I think I've drawn them enough. Okay, and the thing that's tricky in this situation is when you're trying to describe what is happening to this box, intuitively you want to describe some kind of a forward force, because what you see in the car is that you have the box that was sitting here and it flies off to the front to become smush cakes. So you want, as you are trying to draw a free body diagram for this situation, it's quite natural and understandable to want to say, if this is the box of cupcakes, that there's some kind of a force, apply the force. And this is the training that you are going through. Training being learning to identify real forces correctly, and only the real forces correctly, and try to and learn to dismiss forces that are not really there, the fictitious forces. So in this situation, if I'm asked to draw free body diagram of the box, this is the thought process that I need to go through. I need to go through, okay, what forces must be on the box? I know there must be gravity on the box. Box is, it's Earth. So, and I like to get into habit of always drawing gravity. So there's potentially gravity. Well, there's gravity on the box, and the practice I like to go through is this practice, meaning is this practice of drawing forces as it becomes necessary for me to draw them. So as I draw this force on the box, if I have a net downward force, the box must be accelerating downward. And that's not the description of acceleration of the box I have. It's not accelerating vertically. So vertically forces must balance out, which means there must be another force that balances out gravity. That's what we call normal force, support force from the seat. Okay, so the box is not accelerating vertically. And at this point, I ask the question, did I draw all the forces that I need to draw? And this is the point at which some people might be tempted to draw a forward force. And here's the situation you need to justify drawing a forward force. In order for you to identify a forward force, you must have a forward acceleration, or you must have some other backward force that somehow balances out the forward force so that the net force can go in either direction. And it's in this situation where it's important that I identified what the direction of acceleration was. The entire car is undergoing backward acceleration. So the contents of the car are also undergoing backward acceleration. So for this situation for forward acceleration that you might want, you don't have that. If anything, you have a backward acceleration. That would be if the car stayed in the seat. And and so if you think through this situation for quite some amount of time, you might think, hey, shouldn't there be friction force on the box? And yeah, there can be friction force on the box, and that friction force will be pointed backward in order to account for any backward acceleration that the box might experience. So you might ask, how does this box smash to the front of the car then? Um, and that's where you have to convince yourself of the truth of this statement. The box, it doesn't accelerate forward. To the extent that there's any acceleration, it has to be backward because any force that can be on the box is pointing backward. So this situation here, it's best described as the car accelerating backward. And in the situation where a box flies forward and smashes to the front of the car, it's that box is not accelerating backward as much as the car is. So, so the box it doesn't fly forward. At least if you are imagining looking at this from an inertial frame of reference, if a passerby is looking at this box, if anything, this box might be slowing down a little bit, but it's not moving any more forward than it was before the brakes were applied. And because this goes against your intuitive feel for a situation like this, it takes time and effort to think through this carefully. And drawing free body diagram for this can be tricky. But when you've drawn correct free body diagram, you'll have drawn something that looks like this, where there's maybe a backward force that could be pulling the box back a little bit, but at no point you should be identifying a forward force because there's nothing in the setup that could be exerting a forward force. So let me draw this one, mainly because it's a question I like to ask in my physics 10 class, and there are surprising number of forces. So the questions talk about the free body diagram of the book, which is fine, but let me draw the free body diagram of the table and Earth as well. It's one of those questions where there's surprisingly a lot involved. So it asks if a book is located on a table, how many forces should be shown in a free body diagram of the book? Okay, I guess only two. It's not that many. So let me give you a more complete description of the situation. So if a book is on a table, okay, so I have a table, and I have a book on top of it. Well, the table isn't floating out in space. It must be resting on something. It must be resting on Earth. So this is potentially a system of three objects: book, table, and Earth. And this gives you lots of interesting things to consider. So So let me draw the forces on the book, and I will walk through the considerations I go through as I draw free body diagrams. So let me start out with a free body diagram of book. And when I draw free body diagram, as I was saying, I like to draw only the forces that are necessary. And especially for objects on Earth, a good starting place is gravity, because you are always going to have gravity as long as you are talking about either things on Earth or even in orbit around the Earth. Gravity is not gone, so you will still have gravity. So gravity is the force I like to start with. And drawing gravity allows me to ask this question: did I draw all the forces necessary for this setup? And for this setup, one thing I do know is that acceleration is zero. So if gravity is the only force that doesn't work, I must have another force on the book that's going to be balancing out the pull of gravity down. So there must be some upward force. This is what we call normal force, or sometimes support force. But I'll stick with the normal force for most of this class. And with these two forces, the net force on the book can be balanced out to have zero acceleration. So good. Okay, I'm done with the free body diagram of the book. And let me draw a free body diagram of the table. So I have a table, and I will represent it with a dot again, because it doesn't need to be any more complicated than that. So with the table, there's also going to be a gravitational pull on the table. So there will be a gravitational force pulling it down. I got multiple different forces that I'm referring to as gravity. Let me relabel them so that I don't potentially confuse myself. I'm gonna call this W1, W book, weight of the book. And let me call this WT, weight of the table. And a table is not accelerating downward either. So there must be another force that's balancing it. There should be upward normal force. And this would be the support force from the Earth. And I'm labeling two different normal forces. So let me call this N1. Let me call this N2. Okay. Now I'll tell you that I'm missing a force. I'll come back and get that missing force in a bit. But for now, let me just note that this free body diagram is missing a force. But at the moment, going by the criteria that I laid out, acceleration being zero, you could easily convince yourself that this is all the forces you need to consider. Maybe. Let me draw a free body diagram of the Earth, and I'll wrap it up. So free body diagram of Earth. I guess an easy mistake to make for an Earth is to say, Earth is not pulling itself down, so I don't need to draw gravity for Earth. So I could say, I'm done. I don't need to do anything else. Maybe. And this would, this diagram would be consistent with the zero acceleration. And this is the place where I would, I introduced the idea of Newton's third law check. It allows you to identify the internal forces that you could have easily missed when you are first considering your forces on your objects in your system. And remember what Newton's third law says: if you have a force on object A by B, then there's a reaction force on B by A that's equally magnitude and opposite in direction. And I'm drawing these arrows to remind you forces are vectors and the direction matters. So whenever you have both of the interacting objects in your system, you must have those pairs of forces. And here I defined a very large system. So all the forces are internal forces. All the forces there are action-reaction force pairs. So for example, on the book, I drew this weight on the book. I need to identify a matching reaction force. It's not going to be on the book. It's the force on book So you need to identify what object is exerting that force, and if it's weight or gravity, it's Earth that's exerting that force. So there must be a reaction force on Earth. The book is pulling the Earth up by the same amount of force. Now, the Earth doesn't noticeably accelerate upward because of the book, because it's a lot more massive. But in terms of the diagram, there has to be equal and opposite force on Earth. Uh, I have this normal force on book N1, and I don't have any other. Now there are equal and opposite forces, but don't get confused by that phrasing equal and opposite. Even though this force is equal in magnitude and opposite in direction, it's not Newton's third law pair, because Newton's third law pairs have to be on two different bodies. It's a law of interaction. It describes interaction. These two forces are forces on the same body. So as I'm looking at this normal force, I'm asking myself, what object is exerting the normal force? And the book is resting on the table. So it's the table that's exerting the normal force. So there must be a reaction force pair to that force. So that's going to be downward normal force on table of magnitude N1. And I hope if you think this through, it makes a sense that when you consider the table, and when you consider the table with the book on top of it and without the book on top, when the book is on top of the table, there's something pushing down on the table. And this is the force that's pushing down on the table. Newton's third law gives you that nicely. Similarly with this normal force on table, you need to think through what is that force by. It's by Earth, so there must be downward normal force on Earth by the table. So these are the Newton's third law pairs. And I think I have one missing one, the weight of the table. It's the Earth pulling the table down, so the table must be pulling the Earth up. So that's my fourth Newton's third law of pairs. And so for this entire system, there should be 8 forces, 4 pairs, and identifying all of it. Um, so being able to identify all of them correctly without any missing forces or without any extraneous forces. Once you can do that, I think that's a mark of you're having understood Newton's laws, especially Newton's third law correctly. So I would ask you to give that a try, or come up with a similar situation and see if you can reason through it with all the potentially complicated forces that may be involved in all the interactions. This is a video illustration for this example in section 3.5, normal force and tension. So at the end of the chapter is this example of a guy on a scale in an elevator. It asks, what does the bathroom scale read in an elevator? And it describes the elevator accelerating. So what the scale reads, which is the normal force, is supposed to be a little bit different from the weight, which is what you're used to finding. So this is a complete example as far as the descriptions go, but it's quite a bit mathematical. And if you don't have a good intuition for a situation like this, or you have good intuition, it's just not formulated in terms of how we state Newton's second law. If that describes you, then you are the student for whom this video is being made. So let me use this simulation to help illustrate the situation. For this simulation, the drawings are quite simpler. Instead of a person, I have a ball, and instead of an elevator, I have this box with a ball-shaped cavity. This is for the limitations of what I can easily illustrate. So one of these objects, the ball that represents a person, has an option turned on, which will illustrate the force vectors on this object. So right now there's a weight of mg on the ball, and you see that while it's resting on the bottom floor of the elevator, there's a normal force acting upward, which is counteracting or canceling or balancing this weight. And by the way, this falling brief fraction of a second motion, that's free fall. And ouch, and then, you know. All right. So let me move the elevator by applying a force on the elevator. So as the elevator remains motionless, you will see that for the ball or the person in the elevator, it's the same as if it's just resting on the ground. The normal force is an equal magnitude to the weight, and it's pushing it up, counteracting weight. Now, let me adjust the situation a little bit to kind of reenact the scenario that the problem was describing. Let me zoom out a little bit so that I have a little bit of running room. And let me measure the force that I was applying before. So I was applying a force of about, I want to say 170 Newton or so. Alright, so I want to describe as closely as I can the situation where the elevator is not really accelerating. It's moving at a constant velocity. So one way to do that is to apply a thrust that's just barely enough to keep the elevator in suspense, or 170 newtons. Let me give it a little running start up here, and you will see that it kind of floats a little bit, not quite. I guess 170 newton wasn't quite enough. Alright, so 170 newton was just about enough to suspend this whole thing in air. So let me increase that drastically. I think I can actually see it here. Okay, so I'm going to apply 250 newtons. That means there's going to be about 70 newtons of extra force to push everything upward. All right, and let me slow down the simulation speed so that I have more time to talk. And as I run the simulation, watch. So as the elevator accelerates upward, see how the normal force is greater compared to the weight. So the magnitude of weight is from the center here to down here. And the magnitude of the normal force, it's from down here, the point where normal force is acting, to up here. So this normal force is now greater than weight. And that's because just as this elevator is accelerating upward, so does the ball need to accelerate upward, which means there has to be a net force on the ball. And it's the difference between the normal force and the weight that's giving you that net force. Alright, that's exciting. Let me change the situation a little bit. So in this case, the thrust was greater than the overall weight, so that the whole thing accelerated upward. 170 Newton was just about enough force to let it hang. Let me just to make sure that the velocity of this whole thing is 0. So with 170 newtons, this just about barely hangs in the air. And while it's hanging in the air, watch that the normal force is about equal to weight. Now, I am going to reduce the thrust so that there's less than the amount of force needed to let it hang. Let's say 100 newtons. So it'll be about 70 newtons short of what it needs to stay in the air. So it'll accelerate downward. As it accelerates downward, watch how the normal force is less than the weight. Once again, the magnitude of weight is from the center of the circle to the tip here, and the normal force is now about half of that. And this normal force needs to be less because as you watch the whole situation, as the whole elevator accelerates downward, the ball is also accelerating downward. So that means there's a downward net force. And since the weight isn't changing, it's the normal force that needs to change so that there is a downward net force. All right, Let me do a couple of fun things. Let me let it rest on the ground first. I can do that by letting the simulation run with no thrust. Let me give it a little bit of initial upward velocity. I can do that by giving it a little bit of thrust. I guess 250 seems to work well. Let the simulation run for a bit. I think I'm gonna try doing it at regular speed. So let the simulation run. Alright, stop here. Let me zoom out for a bit. And this is what I'm going to do. I'm going to adjust the thrust mid-air. So watch, this entire group of objects have some upward velocity now. It is, mostly upward velocity. And let me change the thrust to the value that will barely maintain the approximately zero net force. Then watch. As this elevator continues to move upward, you see that the normal force hasn't really changed. Or let me flip that around. I think I can do this. With everything selected, instead of accelerating it normally, I can just give it a downward velocity. I think if I'm doing it to all of them, then it'll work fine. Alright, and I'm leaving the thrust at the same amount, 170 newtons. That's what's needed to kind of maintain approximately zero acceleration. Then as this elevator moves downward, watch how the normal force also remains the same. This is an illustration of the principle that it's the acceleration you feel, not velocities. So with this elevator, what affects this normal force or the sensation of weight for the person in the elevator is the acceleration, or more precisely, the net force needed to produce the acceleration that the person should be undergoing, which is tied directly to the normal force. In a previous video, we talked about different types of force. And I want you to make this a separate video for friction force. Because friction force is one of those forces that people struggle with in applying correctly in every situations involving Newton's law problem solving. So I describe the friction as preventing sliding between surfaces. And this is a slightly different phrasing from what you see in the textbook. Let me show you the textbook. So the textbook describes friction as a force that opposes relative motion between systems in contact. And I say friction is a force that prevents sliding between two surfaces, because there are certain situations where friction force will allow motion to occur. And even in those circumstances, if you look at the contact between the surfaces, you will see what the friction does is it prevents the sliding from occurring, or at least it makes the sliding to occur less than it would be without the friction. So both the descriptions do get at the fact that friction will try to stop the sliding between surfaces, but I like my phrasing better because there are those circumstances where preventing sliding actually means causing motion to occur. And the big conceptual piece that I see a lot of people struggling with is the distinction between static and kinetic friction. Now, the distinction itself, I think people can distinguish them fine. What I see people struggling with is how to treat them differently mathematically in problem solving. So, as the textbook description says, static friction is what you have when you have two surfaces that are in contact and they are stationary. So, this is when the friction has successfully stopped the sliding between surfaces. The two surfaces are not moving and exerting a little bit of force. That's when there's a static friction acting. And kinetic friction is when the two surfaces in contact are moving relative to one another. So this illustration is the illustration of kinetic friction. And we put them in these two categories because the mathematical expression telling you what the amount of friction force is, it's different for static friction and kinetic friction. For static friction, this is the mathematical expression. And I want you to note that this is an inequality. What this tells you is the maximum possible amount of static friction force. But the actual static friction force in any given situation can be less. That's what this less than means. Often people forget that this is inequality because in so many of the homework questions and other problems that you get asked, we often ask about the situation that involves the maximum amount of friction force. And because they can encourage somewhat bad habits of always assuming the equality, I want to highlight here that there's an inequality here. Static friction force can be less than the maximum. Now, kinetic friction force is a lot simpler. It's simply given by this equality. It's the coefficient of friction times the normal force. And this figure in your textbook describes this quite well. Imagine you have a block sitting on a surface and you start applying a force. Now, when you are applying no force at all, when you're applying zero amount of force, the amount of static friction force is zero. Because when you're not applying any force, you don't need the static friction force to get it to stay where it is. It's only as you start to apply a force that static friction force increases along with the applied force, so that it's equal to the applied force, and the net force on the object will be zero. This happens up to a maximum value given by the coefficient of friction times the normal force. Beyond the maximum value is where the block will start to move. And typically for most materials, the coefficient of kinetic friction is less than coefficient of static friction. That's what this plot is illustrating. The coefficient of friction force decreasing. And kinetic friction is roughly equal to this value. It's a phenomenological or experimental value, so it's not going to be exact. It'll fluctuate as the thing slides. So if this question makes sense, great. I hope you internalize that. Let me give you one more illustration to help you fully observe this fact that static friction and kinetic friction are different, and that you have to be very careful in determining the amount of static friction. Let me do this with the Algodoo simulation. So here's the simulation. Let me set up a couple of things to help me do this. Okay, so I'm going to draw a bar to serve as my platform for putting the box on. Let me fix one point with an axle, and let me draw a box on top of it. All right, in a minute I'm going to show forces, and I want the forces on the box to show up large. So I'm going to make this box heavier. Let me see if the density of 20 kilograms per square meter will work. By the way, it's kilograms per square meter because it's a two-dimensional simulation. Okay, let me let the simulation run and see how it looks. All right, that seems reasonable. I'm going to try lifting up this end to see how it looks. So this is the flat orientation, and as I lift this end up and up and up. Okay, the box isn't sliding yet. Okay, I guess that's fine. And there's a point where it begins to slide. Okay, I think that's good. So let me go back to the flat orientation again. So let me show the forces here. There's an option to illustrate the forces. And I'm going to unselect many of the forces. Gravity, I guess that's good to have it there to set the scale. I'm not going to have any spring force, but let me get rid of it anyway. Torque, get rid of it. Friction, we do want that. And Don't know why that has letter T. Let me change that to F. Air buoyancy, nah. Controller, we can leave that. So I think that'll show my applied force by hand. Attraction, get rid of that. Axle, there's gonna be a force acting on this axle, and I think it's gonna be distracting, so let me unselect that. Normal force, that's good to have. Air friction, chain, thrust, we'll leave those two external forces on. All right, that looks good. Let's see how the forces look. We'll run the simulation. And yeah, okay, so this is the simulation. And what it's showing is the gravity pulling the box down. It's not accelerating downward because it's being supported by normal forces. And the simulation treats these normal forces as acting at the corners. That's enough to solve the static equilibrium equations and work out the motion. So, and I think there's a friction force here, but it's too small to be seen. Let me start lifting the end here, and we'll see how these forces change. So at this flat orientation, the normal force exactly balances out gravity, and that's all there is to it. And at this orientation, you can see that there's no friction force. It's zero. There's no reason for friction force to be there, and there's no friction force there. Let me start to lift this edge. And at some point, the friction force should be large enough to show up. Let's see here. There's a very tiny arrow there. Do you see the tiny arrow at the corners? Okay, now it's big enough. So it's now big enough to register in the program. You see those friction forces. At this orientation, there isn't a direct relationship between that friction force and the normal force. Watch how between the flat orientation and that angle, the normal force doesn't really change. Because, I mean, it changes the direction, it changes the magnitude a little, but normal force is not increasing, it's not really decreasing that much. But the friction force goes from practically zero to some definitely non-zero value, because right now we are in the regime of static friction. The friction force is whatever it needs to be so that this box doesn't slide. As I continue to increase this angle, the amount of friction force that's needed to keep the box from sliding increases. That's why you see the friction force increasing. And it'll continue to do that up until some angle. At some large enough of an angle, we'll be at such a value of friction force required that the box doesn't stay stationary anymore. At this point, we are in the kinetic friction regime. And if I go back and do this simulation again, let me go back and do this simulation again. What you will see is that once I'm at that kinetic regime, increasing the angle actually doesn't increase the friction force anymore, because once you are in the kinetic regime, then the condition for friction force is different. We can no longer prevent the surfaces from sliding. Instead, what the friction force now tries to do is it'll simply give that magnitude of mu times n, kinetic friction coefficient times normal force. And that force will reduce the sliding a little, but it won't be completely successful, as it is here. So when you're dealing with the force problems involving friction, this is what I recommend. First, to figure out if you are in the static friction regime or kinetic friction regime. If you are in kinetic friction regime, what you have to do is actually quite simple. You just have some amount for friction force, mu times n, and you just use it in your problem solving. If you are in the static friction regime, then you have to be careful that what you have is not an amount of friction force, but what you have is the condition that the two surfaces that you have that are in contact that they don't slide. And the friction force is whatever it needs to be so that the sliding is prevented. And there will be sometimes questions where you can't quite tell if it's a static or kinetic friction regime. Then what I would recommend is make a choice, assume it's one or the other, and just to make sure that after you've worked through the problem solving steps, that you double check if your answer makes sense. If it doesn't, then you have to go back and do it the other way. And hopefully the other answer makes sense. Oh, let me show you the one last thing. So I made a point of saying how I want to describe friction force as a force not that opposes motion, but that it prevents sliding. Because there are these circumstances. Let me see if I have that example in the textbook. Okay, it's not exactly the example I'm thinking of, but this will have to do. So this is a crate on an accelerating truck, and this example is about the crate. So, all right, that's not exactly what I want. I want you to think through what about the truck? The question is describing truck as accelerating. All right, that's fine. But I want you to think about what is causing the truck to accelerate. As you think through that, I hope you will realize that the only forward force that can be on the truck, it comes from the contact between the tire and the ground. The normal force on the tire is not causing it to accelerate, and the forward force in the contact between tire and the ground, that's a friction force. So the way it occurs is the engine, through some transmission and whatnot, tries to turn the wheels. And as the wheel tries to turn, if there were no friction, the tire surface would be sliding against the ground. The friction force tries to prevent that, and in this case, preventing sliding means the wheel and the tire will have to move forward as it rolls. So in this case, you get relative motion between the wheels and the ground from friction. And you can also see actually in this case, the friction force causes the crate to accelerate. And you can describe that as either there being no relative motion between the crate and the truck, or the sliding between the two surfaces, the bottom surface of crate and the top surface of the truck bed, the sliding having been prevented. I think that's everything I wanted to say about friction. Again, I want to repeat the caution that friction force is one of those tricky forces that people tend to make mistakes with. I have an example with a trick question that I've asked in the past. You will see that in a separate video, so watch out for that. So let me use the time to go over really part A of this question, because it's a trick question. Let me start out with the answer, because it's kind of the nature of the trick question, which is where if you know the answer, it's easier. The answer here, the acceleration of the block, it's actually A is equal to 0. And I specifically set up this question that way. You might notice a few suspicious things, because especially on exam questions, I don't like to give numbers. So the things that are suspicious are I'm giving you a specific angle and I'm giving you a specific friction coefficient. And those are all necessary components to set up this trick. So, but you didn't actually have to know that this is trick question. So let me pretend that I don't know the trick and kind of just work through this this question, part A at least. I think part A covers everything I want to say about friction force. So I'll start out with a free body diagram. You've seen me draw free body diagrams many times, so I'll kind of draw this one quickly without a lot of commentary. I have gravity pulling it down, mg. I have normal force, which is going to be perpendicular to the surface. There's friction, so without friction, it tends to slide down this way. So the friction force will have to oppose that. So I'll have some friction force going that way. All right, step number 1. Step number 2, I need to define my axis. That's going to be my x and y. And I need to, that's step number 2. Step number 3, I need to decompose my forces into components along x and y. So x and y. So here you have to be kind of careful with the angles. So let me illustrate the angles that you are dealing with. So this is kind of, the dotted line is the representation of the surface. So if you have this theta here, then this is 90 degrees. So this is actually going to be theta. So in terms of labeling the components, the horizontal component, wait, sorry, no. Did it too quickly. That's not going to be theta because this is the right triangle here. So the angle I have there is not theta, but it's actually 90 degrees minus theta. So this is going to be theta. So which will give me this side here, which is opposite from where the theta angle is. That's going to be given by mg sine theta. So, and this side is going to be given by mg cosine theta. I'm hoping you have seen this enough times that you don't fall into that trap of thinking, oh, x cosine, y sine. Draw the triangle, always start from there. All right, so that's step number 3. Step number 4, write down Newton's second law equations. So I need 2 of them, one for each direction. So I have net force along the x direction. That's gonna be the x component of gravity, mg sine theta, minus the friction force is gonna equal mass times acceleration. And you need a net force along the y direction. That's gonna be n minus mg cosine theta. And this one, from the start, I know will be 0. And as usual, before you call it done, you count your unknowns and equations. I have 2 equations, and I have friction that's unknown. I have acceleration that's unknown. I have normal force that's unknown. And I think a lot of people will get as far as this, saying that, then I need a third equation. And I'm going to get my third equation from friction. And that's going to say my friction force is the friction coefficient times the normal force. And that's the trap that I mean for a lot of people to fall into. And let me show you how you can spot that trap without someone like me telling you that it's a trap. And really the way you spot it is through something that we call sanity check. Whenever you get an answer, you want to make sure that your answer makes sense. So let me go through this. So yeah, I'll go through this. So let me pretend that I think that this will lead to correct answer. And so what I'm gonna do is I have 3 unknowns, and I'm gonna just systematically work through them, eliminating them. So so I want to be able to plug in my friction force there. So that means I need to eliminate normal force here through my equation 2. So let me do that quickly on the side here. My normal force is equal to mg cosine theta. Plug that into equation 3. I get friction force is mu mg cosine theta. I plug that into equation 1. Then I end up with mg sine theta minus mu mg cosine theta is equal to ma. And frankly, you could leave this here or close to here, solve it for acceleration. Say that a is equal to, see that all the masses cancel out, and say a is equal to g sine theta minus mu g cosine theta. But if you left it here, you will have fallen into my trap. This is why, even though a lot of circumstances, this could be an acceptable answer, this is frankly why I keep encouraging you to simplify your algebraic expression. Because simplifying your algebraic expression will give you some insight into the solution. So let me simplify this algebraic expression. I think I can actually do that with the values that I'm given. I'm given the value of mu, that's 1, and I'm given the value of theta, 30 degrees, which means I actually know the values of sine and cosine. I remember enough of my trick to know sine 30 degrees is 1/2, and cosine of 30 degrees is √3/2. So this is going to be equal to, I can factor out g times 1/2 minus mu is 1, √3/2. And this is where I hope you realize that this answer here gives you a negative number. And this is what we mean by sanity check. Does this answer make sense? Usually a negative answer means that the direction of a vector quantity is in the opposite direction to what you're assuming. Here we thought the block would slide down the hill, but I guess what it means, wait, sliding up the hill, nothing's pushing it up. It's not gonna happen that way. So this is what I mean by sanity check. As you're doing the sanity check, you should realize that your acceleration, it cannot be negative because the block is just not going to slide up. So this means this is this is notifying you to the fact that there was a mistake made. So you need to go back and figure out what the mistake is. And the mistake that is made is this: assuming that the friction force is simply mu times n. And if you read through the friction force chapter carefully, what you should have seen is that kinetic friction force is that way. It is really the coefficient times n. There's no other complication there. But the static friction force is more complicated. There's no simple formula that tells you what the static friction force is. There's an expression that tells you what the maximum value for static friction force can be. And for that, you say it's less than or equal to mu(s) times n. But you really have to be careful with this inequality here. This does not it tells you what the maximum possible value of friction force is. It doesn't tell you what the actual value of friction force is. So here, once you realize that, then you actually go back. You realize, oh, I cannot use this. Then you get, so what I really need to fix here is that I wrote this down thinking that I don't know my acceleration, and that would have been the case for kinetic friction. But for static friction, I know it's not sliding, so acceleration here must be 0. And that's how you arrive at this answer here, that your acceleration is 0. And let's see. Oh, and it's asking for the friction force. And what I can tell you is that this equation here, it's still valid. So you can actually, knowing that acceleration is 0, you can actually solve this for friction force to get this expression for friction force. The friction force is equal to mg sine theta. That is just enough to counteract the x component of the gravitational force.